You're listening to Revolution Radio, freedomslips.com, 100% listener-supported radio, and now we return you to your host.
Hello and welcome back to Dave and Mackey's Shiny Setup, show number 510, 10 and 500. This is listener-funded radio, so if you can and feel so inclined, please do donate. It's also cool to just come to the chat room or check out the archives. Buy some of that merch on the website, it's really good stuff. But mostly enjoy the program. And the first hour we've pretty much just, spitballed a few things, a few concepts, a few ideas, just had a conversation. Hopefully you found some of it interesting or even enlightening. That would be great. We are talking, though, the rest of the evening. Well, here, where we are, it's the evening. For you, it's the middle of the night. We're going to talk about the hypothesis. And this is, this is part 58. No, I'm kidding. It's not part 58. Part 10. And we're halfway through. It should be about 20 parts. And if I'm not entirely mistaken, we're talking... I know, right? It goes like that. I know, I hear you, man. But okay, so what's the hypothesis? The hypothesis is what really brings the entire show together, the past 510 shows, why we're doing this, right? And there's a connecting show arc here, and it's expressed by the hypothesis. It is our version, if you will, of what reality, or our attempt to decode reality, to understand really what it all means, and at a very deep level. At the fundamental level, in fact, if we can get to it. We had some epiphanies along the way. We were right about some fairly significant things, which was disturbing and gratifying at the same time. I would have preferred, Dave, if we were wrong, to be honest with you. But we weren't, and here we are. We will talk, though, today about quantum physics, and we did talk about that last week as well. We spoke about the nature of reality. Is our reality in fact real? Do we see anything here that is real? Are we are we living in a simulation? Are we living in a hologram? Are we living in something else as yet to be imagined kind of thing, whatever it might be? And Dave, help me out here. Either we are at equations creating reality, or we are at quantum physics. Our study suggests objective reality doesn't exist. One or the other.
Number 6.
That's what I thought. Okay, so this is really look at a number of items here that seem to point to the fact that reality is not quite as real as we think it is, right? And we discussed with you last week. We spoke about the breakdown of infinite resolution in physics. So we don't have infinite resolution as one. And also the breakdown of infinite resolution in information systems, right? We talked about the simulation argument. We talked about meta as data. And we talked about the computational analog of the observer effect. So if you want to hear more about that, you can go to last week's show. But today, we're going to set out talking about equations creating reality. To cite one of many examples, it has been shown that the negative frequency solutions to Maxwell's equations actually reveal themselves in components of light. Okay, now, just bear that in mind. Were our reality what it appears to be? Solutions to equations should only make sense in the context of describing reality. However, it seems to be the other way around. Data and rules don't manifest from the reality. They seem to create reality.
Number 7. And by the way, Hada! I have to do that.
Hey,
Hanky! That's Mr. Hanky, the Christmas poo from South Park. And it's appropriate, of course, today. No other time, apparently. Not in the lift. Not when a cold caller calls up either, trying to sell me something, or glean information from me. I do it all the time.
How did you get Hanky's number?
You
Hanky, don't play that.
Do you remember when he was a Hollywood star? Yeah. The girls, yeah, that's very funny. So Sorry, we have to digress because it's crazy times. All right,
it's crazy times.
Other computational similarities. Many researchers have also noted that a simulation model solves the prime mover philosophical problem. While the Big Bang Theory implies a universe that arises from nothing, which has no grounding in objective reality, a virtual reality can easily boot up from an external context. In Brian Whitworth's paper, The Emergence of the Physical World from Information Processing, he outlines several additional examples of circumstantial evidence that our universe is a simulation, including, Mickey, did you know randomness and apparent lack of hidden variables?
I did not.
Well, did you know it never made sense to Einstein nor many other scientists that particles would have randomly or would behave randomly like radioactive decay as opposed to following deterministic rules. However, in a computational model, random number generators are a simple concept even in today's systems and can easily be used to drive apparently random behavior. I used to write code. I wrote 6,500 lines of code on a computer system back in the day in a mainframe, and I had to create randomosity of an opponent rather than just strictly Deep Blue or something that would thrash your butt every time you played it, and you still lost. Crazy. Number 3 here, the point 3, probability waves are easy to create. Related to the point above, the probability waves that describe all matter and are responsible for the real effect of quantum tunneling have no basis in objective reality, yet are easy to construct programmatically.
Yes, sir. Finally, the second to last point, as there are 9 here, the explanatory power, or power to explain things. The huge set of well-studied anomalies facing us in fields as varied as physics, entanglement, for example, philosophy, and near-death experiences there, geology, anthropology, and specifically out-of-place artifacts, metaphysics, and specifically again precognition and other phenomena of that nature, and psychology can all be explained only by a programmed reality model. No other theory has that explanatory capacity.
And the last topic here in the group in the group that we're talking about, thermodynamics and the information content of the universe. There is an uncanny similarity to Boltzmann's formula for entropy, which is S equals K times by Ln, little n and little l, then times by, in brackets, W, capital W, bracket, bracket. And Shannon's formula for information entropy is very similar, but it's, best put is H equals E times by minus Ln times by P times by X. In thermodynamics, entropy is proportional to the logarithm of the number of states that matter can be in. In information theory, entropy is proportional to the logarithm of the probability mass function of some random variable. This doesn't necessarily imply that matter is information, just that they behave similarly at a macroscopic level.
Yes, and it is really these coincidences, information, data, matter, energy, and how it's together. I mean, the simplest explanation that I ever heard was that all reality is just created out of thought. So you manifest reality, and I think that is probably the ultimate truth, that we are manifesting, or someone is manifesting reality. We'll get to that when we get to the epiphany and why we are here. not the why we're here at the base level, but why we're here from a pragmatic point of view. We seem to be needed for something, and we'll get to that. But before we do that, there was a study done 2 years ago, and in quantum physics, and that study seems to suggest that objective reality simply does not exist. In a paper recently published, again 2 years ago, in Science Advances, it was shown that in the micro world of atoms and particles that is governed by the strange rules of quantum mechanics, two different observers are entitled to their own facts. Right? So if you look at the last couple of years in politics and media, they go, "Yay! I knew it. My truth is better than yours." In other words, I had to go there. In other words, according to our best theory of the building blocks of nature itself, facts. I'm not talking about ideas or opinions, but facts can actually be subjective. Now, this goes really against the grain of how science understands it. But we're not going to share the entire study with you, but I want to read to you the abstract. Then there's a slightly longer explanation following it. But let's look at the abstract. The scientific method relies on facts established through repeated measurements and agreed upon universally, independently of who observes them. That's really the scientific method, right? You do something in an experiment, and then someone else can do it somewhere else.
Because you really heavily document how you perform the experiment to make it repeatable.
Yeah. Correct. And everybody's happy because it has been proven to be so. In quantum mechanics, however, the objectivity of observations is not so clear. Most markedly exposed in Wigner's eponymous thought experiment where two observers can experience seemingly different realities. The question whether the observer's narratives can be reconciled has only recently been made accessible to empirical investigation through recent no-go theorems that construct an extended Wigner's friend scenario with 4 observers. In a state-of-the-art 6-photon experiment, we realized this extended Wigner's friend scenario experimentally violating the associated Bell type inequality by 5 standard deviations. If one holds fast to the assumptions of locality and free choice, this result implies that quantum theory should be interpreted in an observer-dependent way. Observer, and this is really where the argument was the longest. People, you don't understand the observer effect. You're talking about people and minds. This seems to validate the fact that the observer is absolutely affecting the outcome of an experiment. But Dave, tell us a little more.
Sure. Observers are powerful players in the quantum world. According to the theory, particles can be in several places or states at once. This is called a superposition. But oddly, this is only the case when they aren't observed. The second, well, I shouldn't say the second, the very point of observation by you, of a quantum system, it picks a specific location or state, breaking the superposition. The fact that nature behaves this way has been proven multiple times in the lab. For example, the famous double slit experiment. You've got to know that we've made that problem go away by writing an equation, a probability equation, that just says where something might be found, where it's likely to be found, not where it is found, because we don't know. It's impossible unless we look, and there it is. It doesn't mean the equation was right. Hello. In 1961, physicist Eugene Wigner proposed a provocative thought experiment. He questioned, what would happen when applying quantum mechanics to an observer that is themselves being observed? Imagine that a friend of Wigner tosses a quantum coin, which is in a superposition of both heads and tails, and also landing on the side. And inside a closed laboratory, that is, every time the friend tosses a coin, they observe a definite outcome. We can say that Wigner's friend establishes a fact. The result of the coin toss is definitely head or tail. Wigner doesn't have access to this fact from outside, and according to quantum mechanics, must describe the friend and the coin to be in a superposition of all possible outcomes of the experiment. That's because they are entangled, spookily connected. It's kind of a paraphrasing of Einstein. That was spooky action at a distance. So that if you manipulate one, you also manipulate the other. Wigner can now, in principle, verify this superposition using a so-called interference experiment, or an interferometer is going to be used, a type of quantum measurement that allows you to unravel the superposition of an entire system, confirming that two objects are entangled. When Wigner and the friend compare notes later on, the friend will insist they saw definite outcomes for each coin toss. Wigner, however, will disagree whenever he observed friend and coin in a superposition. That's like the coin is in the air. This presents a conundrum. The reality perceived by the friend cannot be reconciled with the reality on the outside. Wigner originally didn't consider this much of a paradox. He argued it would be absurd to describe a conscious observer as a quantum object. However, he later departed from this view, and according to formal textbooks on quantum mechanics, the description is perfectly valid.
And this is the experiment. The scenario has long remained an interesting thought experiment, but does it reflect reality? And this is really the crux here, right? I mean, you can theorize until the cows come home, means nothing, and that's what Tesla's problem was with a whole bunch of these theoretical physicists.
You can't solve reality with equations.
You cannot. You can do whatever you want with equations, but it might not reflect reality. In any event, scientifically, there has been little progress on this until very recently, when Časlav Bruckner at the University of Vienna showed that under certain assumptions, Wigner's idea can be used to formally prove that measurements in quantum mechanics are subjective to observers. Bruckner proposed a way of testing this notion by translating the Wigner's friend scenario into a framework first established by the physicist John Bell in 1964. Bruckner considered two pairs of Wigner's and friends in two separate boxes, conducting measurements on a shared state, inside and outside their respective box. The results can be summed up to ultimately be used to evaluate a so-called Bell inequality. If this inequality is violated, observers should have alternative facts. Alternative facts. It's. I'm sorry. In my head, funny. I've got all these these media blips from the last 2 years. We have our own facts. We have alternative facts.
Well, it's only Mekki. It's only the way the fish is positioned in the fish tank. So if you head onto the fish, you see the silhouette of a fish's head. But if you see it side on, it's a side-on fish from the side, right? And two people would describe a different object.
Yeah, but they seem to be moving at the same time. Thing.
That's right.
Isn't that weird? Yeah, exactly. But and again, is that where we are? Maybe. Now, we have now for the first time performed this test experimentally at Heriot-Watt University in Edinburgh on a small-scale quantum computer made up of 3 pairs of entangled photons. The first photon pair represents the coins, and the other 2 are used to perform the coin toss, measuring the polarization of the photons inside their respective box. Outside the 2 boxes, 2 photons remain on each side that can also be measured. Despite using state-of-the-art quantum technology, it took weeks to collect sufficient data from just 6 photons to generate enough statistics. And that's with a quantum computer. It would have taken decades, if not millennia, with regular computers. But eventually, they succeeded in showing that quantum mechanics might indeed be incompatible with the assumptions of objective facts. They violated the inequality. The theory, however, is based on a few assumptions. These include that the measurement outcomes are not influenced by signals traveling above light speed, and that observers are free to choose whatever measurements to make. Now, that may or may not be the case. So light speed might not be the speed limit, and observers might not be free to choose what measurements to make, both of which assumptions, if proven not true, would create a whole other raft of issues for us. So let's just go with them here for a second. Another important question is whether single photons can be considered to be observers. In Bruckner's theory proposal, observers do not need to be conscious. They must merely be able to establish facts in the form of a measurement outcome. An inanimate detector would therefore be a valid observer. I mean, that's true. And textbook quantum mechanics gives us no reason to believe that a detector which can be made as small as a few atoms should not be described as a quantum object, just like a photon. It may also be possible that standard quantum mechanics does not apply at large length scales, but testing that is a completely separate problem. This experiment therefore shows that, at least for local models of quantum mechanics, we need to rethink our notion of objectivity. The facts we experience in our macroscopic world appear to remain safe, but a major question arises over how existing interpretations of quantum mechanics can accommodate subjective facts. Some physicists see these new developments as bolstering interpretations that allow more than one outcome to occur for an observation rather. For example, the existence of parallel universes in which each outcome happens. Others see it as compelling evidence for intrinsically observer-dependent theories, such as quantum Bayesianism, in which an agent's actions and experiences are central concerns of the theory. But yet others take this as a strong pointer that perhaps quantum mechanics will break down above certain complexity scales. Now, clearly, these are all very deeply, philosophical questions about the fundamental nature of reality. Whatever the answer, an interesting future awaits. And just to be very, very clear here, you still need a conscious mind to evaluate the observed data. Now, the observer in the first instance could just be a detector, but if no one looks at the detector, then how would you ever know that a measurement took place, if you understand what I'm saying here? But, Mr. Danger, why don't you tell us about quantum
spookiness? So physicists prove quantum spookiness and start chasing Schrodinger's cat. This was published in October 24, 2015 at 1:19 a.m. So you got to think about how remember how we used to work all hours? The world of quantum mechanics is weird. Objects that are far apart can influence each other in what Albert Einstein called spooky action at a distance. And cats can potentially be dead and alive at the same time. For decades, scientists have tried to prove that these effects are not just mathematical quirks, but real properties of the physical world. And they are getting somewhere. Researchers have finally proven in a new study that the link between particles at a distance reflects how the universe behaves, rather than being an experimental artifact. Meanwhile, another team of researchers have set out to show that a living creature, albeit a bacterium, can be in two different quantum states at the same time, just like the cat in Schrodinger's thought experiment. Bell's inequality test. But let's begin with the paper published in Nature, which proves that the world is inherently spooky. All systems described by quantum mechanics can display so-called entanglement. I don't know why they would use so-called in there. They are entangled.
That's
so-called.
right.
I'll give you so-called author.
I'll call you something so-and-so.
I'll call you so-called author. And for example, an electron, like a coin, can spin in two directions, up and down. But two electrons can be entangled so that a measurement of the spin of one electron will define the spin of another. According to quantum mechanics, the spin of one electron cannot be known in advance of a measurement, yet it will be perfectly correlated with the other, even if it's in a distant location. Einstein didn't like this because it seemed to imply that the information could be sent from one electron to the other instantaneously, breaking a rule that says nothing can travel faster than the speed of light. It's more a guideline. He instead thought that there were hidden variables encoded in each electron that could determine the result if only we could access them. But in the 1960s, Northern Irish scientist John Bell came up with a method to test Einstein's theory. Bell's inequality is in inverted brackets, inverted commas. It is satisfied. Bell's inequality is satisfied only if actions in one location cannot affect another instantly, and the outcomes of the measurements are well defined beforehand, something dubbed local realism. And remember, we all know that the entanglement is non-local. Just remember that, put that into context. Bell showed, theoretically, that quantum entanglement would violate his inequality test, but local realist theories containing Einstein's hidden variables would not. This is because the link between entangled particles is so strong that Einstein wanted to believe. So, if the measured correlation between pairs of particles from an experiment was above a certain threshold, it would be incompatible with hidden variables, and entanglement would win the day. Meki.
Bell's theorem. The desire to test this in the lab has driven huge experimental advances in the 51 years since Bell's paper. However, all implementation of Bell tests to date have contained loopholes that have left some wiggle room for the universe to obey local realist theories. One of these was the efficiency of the measurements was too low, known as the detection loophole. Although the data obtained violated Bell's inequality test, it may not be a representative sample of a complete set because some photons in the experiment couldn't be detected. Another loophole was that the measurements were too slow, which is the locality. If the measurement devices were able to communicate via some unknown, slower than light channel, they could share information and influence the outcome of the impending measurement. Yeah. The new study is the first experiment to simultaneously close both of these loopholes in a test of Bell's inequality. The scientists used a laser to make two specific electrons, each within a diamond located over 1 kilometer apart, to increase their energy and emit a particle of light, a photon, which was entangled with the state of the electron. The photons were then sent through an optical fiber to be united at a third location. If they arrived at just the same time, the photons would interact with each other and become entangled, meaning their remote electron bodies would become entangled too. The electron spins were then measured to test Bell's inequality. The two loopholes were closed by ensuring that the efficiency and speed of the readout were sufficiently high. As a result, the team were able to demonstrate conclusively that the universe does not obey local realism. The outcomes of measurements cannot be known in advance, and half of an entangled state can exert spooky action on its remote partner, Dave.
Physics' famous feline. Entanglement is not the only type of unusual quantum behavior. Another effect known as superposition is the ability of a particle to exist in two states, for example, spin or even location, simultaneously, and is now regularly observed in laboratories around the world. For example, electrons have been known to travel through two slits at the same time when we are not watching. The minute we observe each slit to catch this behavior in action, the particle chooses just one. Meki.
Quantum superposition made easy. However, we do not directly observe these effects in daily life. For example, the glass you have cannot be in two places at once, or you would struggle to drink it, of course. But because we don't encounter such bizarre things, it would seem logical that at some scale things switch over from the real world of the quantum to our familiar everyday. And that's really the crux of the issue here, because the quantum world is definitely non-logical, or at least not to our mind. It seems to defy all the rules of common sense, right? But what is the scale at which this switch happens? If we had a technically perfect experiment, would we be able to observe large objects in these superposition states? This is the question posed by Schrödinger's thought experiment, in which a cat is placed in a sealed box with a flask of poison and a single radioactive atom, which will undergo decay at a random time. If the atom decays, the flask is broken and the cat is poisoned. If it does not, the cat lives on. By waiting for the atom to decay, does the cat exist in both states at once, as the atom does? We know that when we open the box, we must find the cat alive or dead, but is it a property of the universe or the observer that makes the cat choose its state? Back to the team preparing to address this very question. Their proposal involves putting a bacterium, rather than a cat, in a state of superposition. Now, to be clear, a bacterium is a living creature, right? Unlike a virus. So, you could very well substitute a cat for a bacterium. Recent technical advances based on superconducting microwave resonators, devices used to detect radiation and for quantum computation, have enabled physicists to observe quantum effects in tiny, flexible aluminium membranes, known as micromechanical oscillators, coupled to the circuits. Tiny membranes, tiny membranes count as large objects in the world of quantum physics, because even with a mass of only 50 picograms, which is 50 trillionth of a gram, they contain hundreds of billions of atoms. However, these resonators have to be cooled to within a fraction of absolute zero, which is minus 270 degrees centigrade, before any quantum behavior emerges. Otherwise, thermal vibrations mask the effects. The team plans to put a bacterium on top of such a membrane, which would then be cooled to its lowest state of energy. The membrane would then be placed into a superposition of two different states of motion, two different types of oscillations. They aim to show that the effect of the bacterium on the properties of the oscillator would be minimal, with the oscillator effectively behaving as if the bacterium were not there. In this way, the bacterium would effectively be in two states of motion at once. Researchers also plan to entangle the position of the bacterium with the spin of an electron inside it. The proposed experiment would be impressive, but mainly for showing that quantum mechanics holds true for objects bigger than subatomic particles. But it seems unlikely to answer whether Schrödinger's cat can be alive or dead at the same time, because the bacterium would remain in a constant glass-like state of cryo, I should say, because it's frozen. If this were the cat, it would exist in suspended animation rather than in a superposition of simultaneous life and death. And just to be clear, if we cool the cat to minus 273 degrees centigrade, it would be very dead indeed.
Yeah, I wouldn't come back from that experiment.
No, there's no coming back from that, Dave. Yeah. But tell us about the final straw.
Causality. Causality disappears at the flick of a switch. Researchers demonstrate superpositions using a device comprising of a single atom. Andrew Masterson reports. Scientists have succeeded in observing one of the strangest predictions of quantum theory, the breakdown of causality. In the macro world, causality is a fundamental property. If one thing happens, it causes another to follow it. For instance, if a tap is turned on, water flows out. Or if a drum is struck, a sound is heard. If this is this, as the saying goes, then that. Sorry, crazy ants. On a quantum level, however, cause and effects breaks down. The weirdness of quantum mechanics means that events can happen without a set of order, and says physicist Jackie Romero from University of Queensland in Australia. To prove this, Romero and colleagues constructed a tiny machine known as a photonic quantum switch, essentially a gate mechanism built from a single atom that can be turned on and off by using a single photon. Such switches were first designed in 2014 by scientists at Harvard University in the US and are seen as critical components for future secure quantum computers. Essentially, by altering the state of a single atom, a flow of photons can either be opened or closed. Romero's team used a quantum photonic switch to demonstrate that two possible operations dubbed A and B can exist in a superposition of their two possible orders. By changing the polarization of the photons, the scientists were able to demonstrate that one did not need to precede the other. In essence, the two operations could happen in any sequence, a condition known as indefinite causal order. Take the example of your daily trip to work, where you travel partly by bus and partly by train, explains Romero. Normally, you would take the bus, then the train, or the other way round. In our experiment, both of these events can happen first. The scientists showed that the order of events occurring with the switch depended entirely on polarization, not causality. By measuring the polarization of the photons at the output of the quantum switch, we were able to show the order of transformations on the shape of light was not set, says co-author Fabio Costa. This is just a first proof of principle, but on a larger scale, indefinite causal order can have real practical applications, like making computers more efficient or improving communication.
Or breaking reality.
That's right. Everything's going to get sucked into a single point, singularity, as soon as they prove it.
Yeah, so to be clear, let's say you're holding a cup of coffee, right? A porcelain cup,
or not holding it,
or not holding it, and you're dropping it, and then it breaks. So what this says is, the cup of coffee did not break because you dropped it. There's no causal relationship between the breaking of the coffee cup and you dropping it.
Because you could be standing there holding the broken cup, and only coffee is on the floor.
That's possible.
Mm-hmm.
It gets really strange. But once you start applying quantum mechanical rationales and realities to the macro world which we inhabit, things become very uncertain. And I believe, as a matter of fact, that in our higher state of functioning, so not in the state that we're in right now, the suppressed or imprisoned state, we can understand and comprehend all of this.
Mm-hmm.
It would be no issue for us to, well, of course, makes perfect sense. But we are limited severely in our present state. And this is one of the key reasons, really, in my opinion, why we, make like a tree and leave this place behind, as it were. But of course, that is harder, easier said than done, and we'll get to how that is possible toward the tail end of the show, how to escape this reality matrix. We do have time, Dave, I think.
Go on.
To start on the next section, because we've discussed the nature of reality, we've discussed history, and we discussed a large number of things, including ancient belief systems. There's one ancient belief system that is older than many others, and that is the belief in reincarnation. But really, guys, reincarnation? What? I mean, so far, quantum physics, yeah, I'm with you. And all the other stuff was interesting, but now we're going into fairyland territory. Turns out, no, not really. And we're going to share significant research here with you of three specific people: Ian Stevenson, Paul Tucker, and Helen Wambach. And Helen Wambach, in fact, went into this field trying to disprove reincarnation, saying, "Oh, what bah humbug! What nonsense this is! Reincarnation, sure. What's next? Eh? The moon is made from green cheese? Well, maybe it is. No, the reincarnation, it seems, is a lot more real than we give it credit. In fact, most, if not all, of the religions that we have today, as well as ancient religions, very much believed in reincarnation. I mean, of course, we know today Hindus, Taoists, Buddhists, etc. They believe in reincarnation. But did you know that the early Christians also believed in reincarnation? And the Gnostics, and which were later named heretics, believed that Jesus was not, in fact, I guess, raised from the dead, but rather reincarnated in his way. Yes, that is the thing. Even the Jewish people had reincarnation as part of the credo. Yeah, I saw that, Dave. And oh, sorry, Dave just notified me, and he's correct that Bishop Desmond Tutu has passed away. He was certainly a mover and shaker in Africa, and I'm sure that his presence will be missed on that continent. Yeah, so reincarnation has been around for a long time, the belief in reincarnation, right? And you ask yourself, well, I mean, we believe this, we believe that, we believe a whole bunch of things. What I found, though, in my life, whenever you come across belief systems, there is a kernel of truth. I mean, otherwise, how do you, how do you substantiate your belief unless there's something to it? Now, turns out that a number of scientists, the ones I mentioned earlier, have in fact started to look into this and looked into this for a long, long time. And we're going to talk about the reincarnation research here. So there was a psychiatrist by the name of Ian Stevenson who devoted the last 40 years to this scientific documentation of past life memories of children from all over the world. This is important here. He researched children not just from backgrounds or cultures that believed in reincarnation, but from others as well. He has over 3,000 cases in his files. Now that's a pretty impressive sample set. Many people, including skeptics and scholars, agree that these cases offer the best evidence yet for reincarnation. Dr. Stevenson's credentials are impeccable. He's a medical doctor and had many scholarly papers to his credit before he began paranormal research. He's the former head of the Department of Psychiatry at the University of Virginia, and now is the director of the Division of Personality Studies at the University of Virginia. And if I'm not mistaken, he was also the inspiration for one of the characters in Ghostbusters, the guy with the glasses, Dr. Spankman. Not Spankman.
Not Spangler.
No, Spangler?
Not Brinkman either.
Brinkman. Well, he was the guy with glasses. He was the guy with the glasses.
Yes. He's passed away though.
Yes, he has. Now, why don't you tell us about? Of course, it is Jim Tucker, not Paul Tucker. Why don't you tell us about Jim Tucker, Dave?
I'm trying to find it.
Tell you what,
is that where it says Tucker, whose research is funded?
No, for nearly 15 years.
Oh, yes. Yes, that's right. For nearly 15 years, Jim B. Tucker, Res 89. Is that when he passed away? What does Res mean?
Resident, I think.
Oh, right. Okay. Thank you. You think, but I believe you.
Yeah.
No. An associate psychiatry professor at the UVA Medical Center's Division of Perceptual Studies has been investigating 2,500 cases made by children, usually between the ages of 2 and 6 years old, who say they've had past lives. The children are sometimes able to provide enough detail about those lives that their stories could be traced back to an actual person, rarely famous and often entirely unknown to the family, who died years before. Tucker's research, based in part on the cases accumulated all over the world by his predecessor, Ivan Stevenson, who died in 2007, has caused little stir. Tucker, whose research is funded entirely by an endowment, began his reincarnation research in the late 1990s after he read an article in the Charlottesville Daily Progress about Stevenson's office winning a grant to study the effects of near-death experiences. I was curious about the idea of life after death and whether the scientific method could be used to study it, Tucker says. He began volunteering with Stevenson's department and after a few years found himself a permanent researcher in the office, where his duties included overseeing the electronic coding of Stevenson's reincarnation cases. That coding took years. Stevenson's handwritten case files reached back to 1961, but Tucker said the work is yielding intriguing insights. Roughly 70% of the children say they died violent or unexpected deaths in their previous life. Males account for close to 3/4 of those deaths, almost precisely the same ratio of males who die of unnatural causes in the general population. Most cases are reported in countries where reincarnation is part of the religious culture, but Tucker says there is no correlation between how strong a case is deemed and that family's belief in reincarnation. 1 out of 5 children who report a past life say they recall the intermission, the time between death and birth, although there is no consistent view of what that's like. Some allege they were in God's house, while others claim they waited near where they died before going inside, well, their mother. In cases where a child's story has been traced to another individual, the median time between death of that person and the child's birth is about 16 months. Further research by Tucker and others has shown that children generally have above average IQs and do not possess any mental or emotional disorders beyond average groups of children. Nothing statistically significant. None appears to have been disassociating from painful family situations. Nearly 20% of the children studied have scar-like birthmarks or even unusual deformities that closely match marks or injuries the person whose life the child recalls received at or near his or her death. Most children's claims generally subside around age 6, coinciding roughly with what Tucker says is the time children's brains ready themselves for a new stage of development. Despite the otherworldly nature of their stories, almost none of the children exhibit any signs of being particularly enlightened, Tucker says. My impression of the children is that while a few make philosophical statements about life, most are just typical kids, he says. It might be a situation similar to not being any smarter on the first day of first grade than you were on the last day of kindergarten. That's a very good analogy. How exactly the consciousness, or at least memories, of one person might transfer to another is obviously a mystery, but Tucker believes the answers might be found within the foundations of quantum physics. Physics have long known that matter like electrons and protons, or photons for that matter, produce events only when observed. A simplified example, take light and shine it through a screen with 2 slits cut in it. Behind a screen, a photographic plate that records the light. When the light is observed as it travels, the plate shows it went through both slits. That's unobserved. But what happens when the light is observed? The plate shows the particles go through just one of the slits. The light's behavior changes, and the only difference is that it is being observed. Therefore, there's plenty of debate on what that might mean, but Tucker, like Max Planck, the farmer of quantum physics, the father of them, it believes that discovery shows that the physical world is affected by and even derived from the non-physical, from consciousness. If that's true, then consciousness doesn't require a 3-pound brain to exist, Tucker says, and so there's no reason to think that consciousness would end with it.
Which of course completely upends which completely upends the mainstream's view of reality and scientific progress, and in fact the world at large, because everything is grounded in the physical material world that we live in. People have long argued, if there were a soul, could it survive without a body? The body is clearly needed, la 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 la. Now it seems reincarnation says no. The body is just a vehicle. And this is really what's fundamental to the hypothesis also. The body, more than a vehicle, is, of course, our prison. It is the box into which we've been shoved, much to our chagrin, but nonetheless, here we are. And in order to ensure that we do not escape this prison, and we don't get any smarter either, I guess, because the longer you're in a prison, the more likely it is that you figure out a way to escape. We die. And when we die, all of our knowledge, memories, etc., is mostly wiped out. Now, a few thousand cases, even 10,000 cases, is only a drop in the ocean if you compare it to the total number of humans in existence. And you can see it's a vanishingly small percentage of people therefore retain their memory of past lives actively. Under regression, a lot more people do. If you hypnotically regressed, a lot more people remember it. Now, there's some suggestion that some of it is induced by the hypnotist and other things, but a lot more of us remember. But very few of us remember it actively. Children seem to be, before the age of 5, remembering it. Again, only a small, tiny percentage, really, looking at the total numbers. But nonetheless, a significant enough number to really consider reincarnation as a thing, as something that happens. And next week we shall see that Dr. Helen Wambach, who in fact set out to prove how nonsensical this whole idea of reincarnation is, was in fact completely turned around on the subject when she started investigating in earnest. And that's really what should happen when a scientist goes out to, even if you try to disprove something, that's cool, there's nothing wrong with that, right? As long as you follow the evidence, as long as you follow whatever the science tells you, right? That's good science. If it doesn't coincide with your belief system or the belief system you had before you went into the research, and it forces you to change your mind, that's good science. That is good science. Because you have to follow the data. You have to follow the facts. And as we shall see again next week, when we go into this a bit more deeply, reincarnation truly is a phenomenon that cannot be dismissed. And it is not just a phenomenon, Dave. This is important to understand for everybody.
Mm-hmm.
It is not just a phenomenon for people or cultural environments that believe in reincarnation.
That's right.
Yeah, these kids or these people that are part of these these studies, this I guess body of research, come from all walks of life, all cultures, all linguistic backgrounds, Christian, Muslim, Hindu, whatever have you, atheist, in fact. And it is therefore, we can't say that this is a culturally expected kind of outcome. Right? If you went to India and everybody had these recollections, you go, well, Hindus believe in reincarnation anyway. There's a cultural bias, blah 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 blah, and you would probably dismiss it because it would conform with the idea that in India everybody should believe in reincarnation if they're Hindu. Now this is not this. This is everybody all around the world from completely different backgrounds. Some people not even aware, and certainly if you're age of 5 or 6, reincarnation is not something that you would have come across necessarily as a thing you discuss. Your peers or even your family. You might have overheard something, but chances are that you don't have a great or deep understanding necessarily. You may, but chances are you probably don't. Now, there's only 1 minute left. So once again, and then I'll hand it over to my esteemed colleague to close it out. But everybody enjoy your midwinter Northern Hemisphere solstice. It is a time of regeneration. It is when the ancients believed the sun was reborn after 3 days of teetering on the edge. Is the sun going to come back? Yeah, it came back. Hurrah. And ancient cultures all around the world have and will be celebrating this particular day for ages yet to come.
This has been another Shiny Side Out with Dave and Mekki. Stay tuned for something. I don't know who it's going to be. It could be. It could very well be Jer Bear with After Hours, but I'm not sure what the schedule has in store for us. But anyway, stay safe, be nice to everybody, and we'll catch you next week for another Shiny Side Out with Dave and Mekki. Take care, everyone.